Welcome to this lecture of calculus. In this lecture, we shall study what we mean by a bounded function, and then we shall prove the boundedness theorem for the continuous functions. So first we begin by defining what we mean by a bounded function. So this is a definition. Bounded function. A function f is said to be bounded above on an interval I if f of x is less than or equal to k for all x in the interval I, where this k belongs to the set of real numbers. So this means that we say a function f is bounded if f of x is less or equal to k for all the values of x in the interval for some positive real number k. And similarly, a function f is said to be bounded below on an interval I if this f of x is always greater than or equal to k for all x in the interval I, where this small k is again a real number. So therefore, if we have a function that is always less or equal to some real number k for every value of x in the interval, then we say the function is bounded above. And if the function has the property that it is greater or equal to k for some real number k for every x in I, then we say the function is bounded below. Now finally we can define what we mean by a bounded function. So therefore a function f that is bounded below as well as bounded above is called a bounded function. Now let's take up some examples of bounded functions. The first example that we shall take here is we define a function f of x is equal to x on the interval I, which is equal to suppose 0 to infinity. Now if we define this function, then we can clearly see that f of 0 is equal to 0, f of 1 is equal to 1, f of suppose any real number is the same real number where the real number belongs to the interval 0 to infinity. So we can clearly see that the least value of this f of x is 0, and it will reach infinity at infinity. So clearly this 0 is less than or equal to f of x, and it is less than infinity. So hence this f of x is bounded below, this is bounded below by 0, but the function f but is unbounded above. So this was one example of a function which was bounded below but not bounded above. Similarly, now take another example. We can define a function, suppose f of x is equal to like x squared. Suppose let us define it from minus infinity to some real number, suppose 5. For this function, we can see that this function again assumes only the positive values on this interval, and the smallest value that this function will assume is 0. So then at x equal to 0, we obtain f of x is equal to f of 0. So this is equal to 0 square is equal to 0. But since x square makes every non-zero real number a positive real number, so the smallest value that this f of x assumes is 0. So hence again the function is bounded below but not bounded above. And as x tends to minus infinity, then x square tends to infinity. So therefore the function f of x equal to x square is bounded below by 0 but is unbounded above. Now let's take up another example, the example number 3. Take a function f of x which is equal to suppose sin x. Define it on the set of real numbers. Then we know that minus 1 is less or equal to sin x, and this is less or equal to 1 for all x in the set of real numbers. Thus this function f of x is equal to sin x is a bounded function because it is bounded below as well as bounded above. And similarly, one another function, suppose f of x is equal to 1 divided by x, defined on the interval 0 to 1. is unbounded because as x tends to 0, then this f of x, which is equal to 1 by x, this will tend to infinity. And we can clearly understand that in this way, that when this x in the denominator gets closer and closer to 0, this 1 by x gets very, very large. So therefore, f of x equal to 1 by x tends to infinity as x gets closer and closer to 0. So therefore, this function is unbounded. F of x equal to sin x is bounded. Similarly, x squared is unbounded on this interval, and x is equal to I is unbounded on 0 to infinity. Now let's take one final example here. So we can define a function. Suppose f of x is equal to x squared plus 2x plus 2. Suppose this is defined on the interval I, which is defined on finite interval, suppose minus 2 to 3, then this function is bounded. Now let's take the theorem which we call the boundedness theorem for continuous functions. So this is the boundedness theorem. The theorem states that if a function f is continuous on a closed interval, if a function f is continuous on a closed interval, suppose I equal to a comma b, then f is bounded on ab. Now let's take the proof of this theorem. The proof that we shall take up here uses the Bolzano-Weierstrass theorem, so we shall just mention the statement of the Bolzano-Weierstrass theorem here. So this is Bolzano-Weierstrass theorem. This theorem states that every bounded sequence of real numbers has a convergent subsequence. This is the theorem that we shall use for the proof of this boundedness theorem. This theorem actually makes the proof of boundedness theorem very, very easy. So that's why we are going to use the Bolzano-Weierstrass theorem for proving the boundedness theorem. So now let's begin the proof. So we shall prove the boundedness theorem with the help of a contradiction. So we prove by contradiction. Assume that f is not bounded on AB. Assume that f is not bounded on the interval a comma b. Since we are going to prove that f is bounded, and we are going to prove this theorem by contradiction, we shall assume that f is not bounded and see what happens then. So now what we mean by a function is not bounded on AB, this means there exists a point, suppose xn belongs to the interval a comma b such that f of xn is greater than n for all n belonging to the set of natural numbers. तो इसका मतलब हम यहाँ पे ये ले रहे हैं that if the function f is an unbounded function on AB, so फिर हम इस इंटरवल में एक पॉइंट निकाल सकते हैं xn जिसको हमने नाम रखा, और इस xn पे फंक्शन का वैल्यू बहुत ही बड़ा होगा. तो इस तरह से हम एक सीक्वेंस कंस्ट्रक्ट कर सकते हैं. in this way we can construct a sequence, और सीक्वेंस हमें इस तरह से मिल जाएगी like x1 x2 and so on, and the sequence has all of its terms inside the interval AB such that this f of xi, this is greater than n for all n belonging to the set of natural numbers. तो यहाँ पे अब हम ये ले रहे हैं कि अगर हम एक xn पॉइंट निकाल सकते हैं AB में at which the functional value is very very large, तो इस तरह से हम फिर एक पॉइंट सपोज x1 बनाएंगे, फिर x2 बनाएंगे, such that हर पॉइंट पे f of x का वैल्यू बहुत ही बड़ा होगा. Now, since every point of this sequence x1, x2 and so on, they all belong to this closed interval AB, so therefore this sequence is a bounded sequence. तो इसका सबसे जो largest term होगी, it will be the interval, it can be at most the point B, और इस sequence में जो सबसे smallest possibly value होगा, it will be the point A. But A and B are both finite numbers, so therefore all the numbers x1, x2, xn, whatever in the sequence, they are all finite. So we can say clearly this sequence x1, x2, so on is a bounded sequence. And now here we can make the use of Bolzano-Weierstrass theorem, which states that every bounded sequence has a convergent subsequence. Hence this sequence, by Bolzano-Weierstrass theorem, this sequence has a convergent subsequence दिस सीक्वेंस जिसको अब हम इस तरह से डिनोट करेंगे xn हैज़ ए कन्वर्जेंट सब सीक्वेंस, और इस कन्वर्जेंट सब सीक्वेंस को हम इस तरह से लिखेंगे xnk such that this sequence xnk converges in AB, converges suppose to a point C, which is a point in the closed interval a comma b. Now since f is continuous, therefore the sequence which is f of x and k, this converges to f of c. But since the sequence f of x and k is convergent, and by the definition of convergence, it means that f of x and k must be bounded for every nk. So by definition of convergence, this means that f of x and k is bounded for every nk, for every x and k. तो अब अगर फंक्शन f continuous है तो sequence f of x and k, this will converge to f of c, and x and k here converges to c, then f of x and k will converge to f of c. This is by the definition of continuity. लेकिन जो definition of convergence है, अगर ये f of x and k converges to f of c, it means that every term in f of x and k must be a bounded term. Otherwise, the sequence cannot converge. So, but this is a contradiction. क्योंकि हमने ऊपर assume किया था that f of xi is greater than n, और xi जो अगर हर xi के लिए f of xi is greater than n, और जो ये xn k है वो हमने यहीं से लिया था x1 x2 x so on से, तो f of xn k भी greater than n ही होना चाहिए. So that is in other words f of xn k भी unbounded होना चाहिए. लेकिन यहाँ से हमें मिल रहा है f of xn k is bounded. So this is a contradiction because we had assumed this f of xn, this is greater than n for all n belonging to the set of natural numbers. So this contradiction is because we had assumed that the function f is not bounded. Hence the function f must be bounded. Therefore, f must be bounded. So hence we have shown that if a function is continuous on a closed interval, then it must be a bounded function. Now again, let's take up one example here. So choose a function f. Suppose this is equal to x square plus 1 defined on the closed interval, suppose minus 3 to plus suppose 4. We can randomly choose one closed interval. Then the smallest value of, then the least value of f is f of 0, which is equal to 1, and largest value of f is f of 4, which is equal to 16 plus 1 equal to 17. Hence, this 1 is less than or equal to f of x, it is less or equal to 17 for all x belonging to the closed interval minus 3 to 4. तो जो हमने यहाँ पे ये क्लोज इंटरवल डिफाइन किया और फंक्शन हमने ले ली है एक्स स्क्वायर प्लस 1. नाउ सिंस दिस एक्स स्क्वायर मेक्स एवरी नंबर इन दिस इंटरवल पॉजिटिव, क्योंकि स्क्वायर है यहाँ पे, तो इस तरह से इस फंक्शन का जो स्मॉलेस्ट वैल्यू होगा दैट विल बी ऑब्टेन्ड एट x इक्वल टू 0. और फिर अगर हम x इक्वल टू 4 सब्स्टिट्यूट कर लेंगे, 4 इज़ द लार्जेस्ट वैल्यू इन दिस इंटरवल, तो f ऑफ 4 विल बी इक्वल टू 17. तो इस तरह से f ऑफ 0 इस इंटरवल में f ऑफ x का सबसे स्मॉलेस्ट वैल्यू है, और f ऑफ 4 विच इज़ इक्वल टू 17 ये इस इंटरवल में इस फंक्शन का सबसे लार्जेस्ट वैल्यू है. तो इस तरह से जो फंक्शन f ऑफ x है उसका स्मॉलेस्ट वैल्यू है 1 और लार्जेस्ट वैल्यू है 17. बाकी सब पॉइंट्स पे जो भी वैल्यू हमें मिलेगा इट विल बी ग्रेटर देन और इक्वल टू 1 बट लेस और इक्वल टू 17. सो देयरफॉर द फंक्शन f is bounded by 1 and 17, hence the function f is bounded. And we can clearly see that the function f equal to x squared plus 1 was a continuous function defined on a closed interval, and this obviously also bounded. So with this example we conclude this lecture.